Okay, I just stumbled onto a Rust LLM built from scratch, pure Rust with Endere powering every matrix move. No PyTorch, no TensorFlow, just hand-rolled learning.
Wait, seriously. A model built in Rust that trains through its own transformer blocks. It's like assembling a tiny neural engine by hand, in plain code.
That's the hook, but the project itself calls it a toy, not production grade. Still, what does from scratch actually teach us beyond curiosity?
Great question. It teaches transformer anatomy, gradient flow, and the value of modular design. But scale, data, and optimization stay intentionally limited.
Like a piano student practicing scales on a toy keyboard, functional but not ready for a concert. I wonder how the three transformer blocks feel in practice.
Exactly. 3 blocks keep things approachable, yet real models stack dozens to hundreds. Depth matters for context and nuance.
Right, and that makes the architecture flow. Tokenization, embeddings, transformer blocks, then output projection, classic layered pipeline.
Plus a dynamic vocabulary built from training data, with custom tokenization that handles punctuation. Clever for a Rust project, not a production tokenizer.
Training details fascinate me. Atom optimizer, gradient clipping, 2 phases, pre-training then instruction tuning with modest learning rates.
One can see why they cap gradients at 5. Stability matters in toy models too, yet that cap stifles exploration and learning dynamics.
Plus, no PyTorch means re-implementing layers in Rust. Ambitious, impressive, but challenging for performance and long-term maintenance.
Agreed. The modular layer system and tests help, though the lack of persistence means sessions vanish. Great for experiments, risky for reuse.
Interactive mode after training is neat. It's like a mini REPL for AI. You type prompts and you watch the model respond in real time.
The quick start steps carve a clear path. Build vocabulary, pre-train, instruction tune, then test interactively. Great reproducibility.
Still not production grade is a meaningful caveat. Real-world use demands safety, evaluation, and robust sampling strategies.
Speaking of evaluation, I wish there were perplexity measures or benchmarks. It's hard to gauge progress from DMOS alone.
True, without robust metrics, progress feels qualitative. The tiny sequence length 80 also narrows context and coherence.
And hardware matters. Pure Rust on CPU, no GPU acceleration. Performance here is educational, not a showroom for speed.
It's like teaching a kid to ride a bike with training wheels, learn mechanics first, then test speed, balance, and prompt fuzziness.
Relatable. The small max sequence and greedy decoding reveal limits in long conversations. Smarter sampling could help, if data allowed it.
Greedy decoding is a double-edged sword, fast but prone to dull outputs. Beam search or TopK could fix that if you scale data appropriately.
Implementing beam search or sampling in pure Rust adds complexity. They kept it simple to stay accessible and educational.
Vocabulary building is like teaching a child new words every day. You need diverse data to avoid brittle generalization or odd word choices.
Data scope is tiny by modern standards. Generalization hinges on architecture cues, regularization, and training schedules, so caveats abound.
Gradient clipping stabilizes training, but might suppress rare large gradients that help escape local minima in risky regions.
Tests cover LLM, transformer, attention, embeddings. Great confidence boosters, yet tests won't prove real-world usefulness or safety.
Areas for improvement list multi-head attention, row P, and better optimizers. It's a map for future contributors, not a finished product.
Model persistence is flagged as high priority. Being able to save and load trained parameters would unlock real experiments and longer sessions.
That would raise questions about determinism and versioning. Keeping formats consistent would become a feature, not a footnote.
There's also data leakage risk across saves. You'd need checks, checkpoints, and validation to avoid leaking prompts or sensitive info.
I love the education angle. Building from scratch demystifies LLMs, showing it's not magic but stackable components and careful engineering.
And the purity angle. No PyTorch means it's pure math and Rust, a compelling path for learners who want to see the math behind the magic.
World knowledge examples like sun rises in the east, gravity, mountains. These come from pre-training. Instruction tuning adds conversational behavior.
That two-phase regimen matters. Pre-training builds general knowledge, instruction tuning adds alignment and improves interactive style.
With only 3 transformer blocks, embeddings, and an output projection, you get a playable sandbox. Depth is a trade-off between simplicity and scalability.
Hardware independence here is appealing. You could run this on CPU everywhere, though real performance would demand GPUs or accelerators.
Dynamic vocabulary means evolving tokens too. Imagine tailoring vocab on the fly as you ingest new concepts. A clever trick, but tricky to manage.
Test coverage across LLM, transformer attention embeddings is commendable. Still, real-world robustness needs stress tests and safety checks.
What's the most surprising takeaway for you, beyond the pure DIY vibe? Did any detail flip how you picture the journey from tensors to language?
Honestly, the emphasis on educational clarity is surprising. It's a living blueprint showing where production stacks would hide complexity.
Yep, but the counterargument is we might be oversimplifying. Real systems demand data pipelines, guardrails, deployment plumbing, and monitoring.
True, the project signals potential but not sufficiency. It invites collaboration to tackle persistence, optimization, and evaluation gaps.
Peak insight, the from scratch story crystallizes a truth. Learning how LLMs work out loud demystifies AI even if the model stays tiny.
And the broader implication resonates. You could prototype safer, auditable AI by building transparency into each layer from tokenizers up.
So if we put this all together, the journey is less about raw power and more about disciplined design, testing, and iterative refinement.
Exactly, but the caveat remains. Not every neat idea scales, and evidence for claims is often nuanced or mixed in practice.
That skepticism is healthy. We should push for persistence, smarter sampling, and stronger evaluation before cheering too loudly.
Agreed. If contributors push persistence, better sampling, and robust evaluation, this Rust path could become a shared learning playground.
Before we wrap, imagine a future where a Rust-based LLM toolkit stays readable, debuggable, and testable at every layer imaginable.
That future might be here in seed form. The real question is who will push it toward robust, trustworthy AI built in Rust.